Hello. Following our sequence of videos, in today's video I'm going to show you how to read the DAP file, one of the main outputs of the lvm-dap analysis, using Python and the codes that we have provided with the lvm-dap package. The other day I showed you what's the shape of, the composition of this file. It was a series of extensions, and how you can, there are a sequence of extensions that are fits tables, and how you can read them using a standalone tool like Topcat or any other tool. Of course, you can develop your own tools for doing that, but we have created a simple script in Python, a simple function that load all the content in a single table, and so you can use all the Python tools for making analysis. Of course, you can use your own tool if you want. So basically, the script or the function that is used to read the DAP file, it's this one. It's in DAP tools, the lvm-dap tools. You can import this read the DAP file. Simple to understand. We import another ones like the matplot.dap. I think for the name it's obvious that this tool is used to plot maps, and it's important to import this scatter. That is a wrapper of the matplotlib scatter with some other options included. So we proceed. Basically, we import all the required functions for working with that. There is a function that I'm going to load in here. This tools. It's a Python package that I do for collecting the different tools for plotting and for convenient, and that was the search column. That is a tool that you will see. It's a function that allows you to identify which columns of a table have a certain portion of a name, so it's easy for plotting one value versus another, because tables are large and the number of columns are huge, and they sometimes are difficult to find. So we simply indicate the directory and the file name, and the program runs in a very simple way. The function is just the output. It's an AstroPy table. If you are more used to pandas, for instance, you can transfer that output into a pandas table, and then you use your own tools for whatever is convenient. But so far, the output is an AstroPy table, and it's an AstroPy table that is basically putting together, joining all the tables that I described the other day into a single table. So I'm going to run it with the verbose true. So when you run in this way, it takes a little, because it's not only reading the file, but reading each extension, but as I told you, joining one to the other, ordering them in a convenient way. So in the verbose, it's describing what is reading. It's and the content of each table that is read. That is the same table that is described the other day, apart from the header. That's not needed anymore here. This is the position table, and then the RCP table. I'm not going to explain again what was the content of these tables. Then we have the PAOR. It's a reordering of the emission lines properties derived using Gaussian functions in a way. Remember from the video of the other day that the format was that it was for each fiber It has a different column for different emission lines, but there are different rows for different emission lines, and that's not very convenient when you want to have a single table where one row corresponds to one fiber with all the columns, and not having different columns, different rows for the same fiber. No, so this is reordered in a way that it will be one fiber and columns for each property of the emission line derived with the Gaussian function. And this is the name of the properties derived for the Gaussian fitting. Then we have the same format for the second fitting with the Gaussian functions. Remember the previous videos. And then we have the blue, red, and infrared tables that include the analysis using the weighted moment analysis for the emission lines. Again, in the same format, the ID and the different properties, the blue, the red, and the infrared. So as you can see, the number of columns is quite large. Then it reads the coefficients of the decomposition in the RCP for each fiber. And go to that. Then the sigma and chi-square, it was the additional table that I explained the other day, where we have the velocity dispersion corrected for the instrumental resolution in kilometers per second for all the different emission lines, and the chi-square of the fitting for all the different emission lines. And in all cases, the same name for the emission line is shared in between tables, in between columns. So it's easy to identify. I will show you how a particular entry or all the entries for the same emission line. So it's basically loading all this, okay? And at the end, it creates, let's insert a cell. It's a considerably large table, no? So if we show it in the usual way, well, it has the length is the length of the number of fibers, and the number of columns here, it's quite large, no? So let's see if we can visualize that. But you can see that then it's really a huge number of columns, and each row corresponds to one single fiber. So since there is a lot of columns, sometimes it's a bit difficult to identify, for instance, all the values that correspond to one single line. Let's say, for example, to H alpha, no? So we're trying to identify all the columns that contain the values for H alpha. So for doing that, we use this tool that I indicated, or this function that I indicated before, that is a search column. So I'm going to put here search, recommend that, search column, search call, better to say, the table, and the string that we want to look for. And as you can see, this is the list of columns that contain information for the H alpha line. This is the flags of H alpha derived using the non-parametric fitting. Here is the flags using the parametric fitting in the first fit. This is the flags using the parametric fitting in the second fit. And then the velocity dispersion. So you see that this is the velocity dispersion in kilometers per second corrected for the instrumental values. And now that we have identified these columns, we can, for instance, try to plot one against the other, no? Like let's say uh, let's say then x well scatter the double BP. That's the non-parametric second parametric in the x-axis, and the non-parametric flux, no? For instance, what I just said, what I made wrong, fixed size. Well, that's very simple thing. Okay, so then you can compare the values derived for the parametric and non-parametric analysis for this line. This is just a very simple example. I'm going to plot from 0 to the and straight line in the one-to-one. Let's just to check. Maybe we have surprise here and it doesn't follow the one-to-one. Well, and as you can see, there are some deviations, but this deviation have to do with the fact that the two analyses are different. And if there are some asymmetries in the emission lines, the fluxes derived from one in one way or another are going to be different. And that's could be relevant if we compare also the velocity dispersions and we have a different velocity dispersion, then we will check the lines and maybe we have an asymmetry in the emission lines. But in general, there is a very tight correlation between the two values. Now we have this tool, this plot, matplot DAP RGB, is to create RGB images using three fluxes or three parameters. So the way that it runs basically is that you run this script, you indicate the table, and you indicate which columns corresponds to red, blue, and green. Well, no, RGB, red, green, and blue. And you can scale the values in this column by a certain scaling factor. In this case is 111, and this is nitrogen, H alpha, and oxygen 3. So it's a three-color image created using these three bands. The title, basically is the legends of the red and the green and the blue. And some parameters that control the fixed size and the directory where this is stored. So you can create for the parametric fitting and for the non-parametric fitting. And as you can see, the parametric fitting in some fibers has failed, and it could be worth to check for which reason this happened. Remember that this is the Helix Nebula, the data that we have distributed, and they are not the final most perfect data reduction, but the image that you can derive when you use the non-parametric fitting, it's really quite good. We can use another lines. Here, red is the sulfur line. So of course the distribution of colors is different. Well, that's just a simple tool to create RGB images. And as you can see, this is a scatter plot, so you don't need to interpolate to create this kind of plots for signs. We can't plot a BPT diagram. that you know that the meaning of the BT diagrams when the spatial resolve information below the scaling of the site, the typical size of an S2 region, that is the case of the LVM data, cannot be interpreted like we do in extragalactic astronomy. But anyway, that should be interpreted in a completely different way. So that's another BPT diagram. In here, I can tell you that we have a problem with oxygen 1, and that's a problem with the sky subtraction in the case of this data that we discovered later. And I have to correct that. I have corrected that in this other script. So I will share both scripts to show you how this has been corrected, the fluxes. What I do here is that I identify which are the lines that have this higher signal to noise to create a table of the signal to noise for the different emission lines, and I identify as good those that have a signal to noise above 45, for instance. And that's this table. This is the order by the peak signal to, well, they are not ordered by the peak signal to noise, but they are all above signal to noise above 45 could be the good ones. And so, and I take the 36 one that have a very high signal to noise. I plot this where you can identify the signal to noise versus the wavelength, so you can see which lines have a higher signal to noise. Of course, apart from plotting the RGB image, you can plot, and that's what it does, this other script, plot a single map of a certain property. This is the same as before, but it includes the possibility to select the axis where you plot that property. And let's see here. Well, yeah, that's interesting. I'm plotting here the oxygen 2. That's not oxygen 2, that's nitrogen 2, sorry. Let's change that. It's nitrogen 2. My fault. Sky, nitrogen. Where's the other one? That's okay. This is to illustrate that oxygen 3 has oxygen 1 6300 has a problem in the sky subtraction. If we look for the integrated spectra, we see that indeed there is an emission that is a remnant of a sky emission. This is the shape of a nitrogen 2 6548, the weak one, that should have an intensity similar to that one in the same intensity level. And as you can see, there is a clear structure where we have this ring of high intensity, lower intensity in the center. So this is like a bubble for the initiation structure of nitrogen. And then you go down to a very low value in the outer part. When you plot that for oxygen 1, you have a high intensity value almost everywhere, and that's because we have a defect in the sky subtraction. If we attempt to correct that, selecting regions where you should have very low signal to noise for oxygen 1, and you subtract this value, you can see that now you can recover a structure more similar to what you should have or you have with nitrogen. So that is an attempt to make a correction a posteriori, assuming that the outer part of the pointings that we are using should not have any flux intensity in the considered line. Of course, when you have the very good better reduction, this should not happen. But for the public data that we are distributing, this is indeed something that is required. Just to illustrate how to do that. And we can plot all the emission lines above a certain signal to noise. So this is a mean flux. Now it's the mean flux and the error. So this is ordered by signal to noise, and when it's go from the strongest or highest signal to noise to a much lower signal to noise. And as you can see here, Oxygen 1 have this problem that I indicated before clearly, have a problem with the subtraction. And there are other lines where we have this problem with the subtraction. So if you apply the correction that I showed you before, well, I don't know if this is the corrected one. Well, that's still not the corrected one. But once you apply the correction, this disappears, and apparently I have not stored the corrected one. But that's the way to do that is just to select the region where in the outer part we have low signal to noise. You make the average and you subtract. It's in the code. Okay. Well, so this is the highest signal to noise, but you can create similar maps for all the lines. So it takes a while, but it's going for the highest signal to noise to the lower signal to noise to all the lines. The analyze using the non-parametric fitting, and you can see that there are different shapes for different emission lines, and in helium and iron, for instance, the higher intensity is in the center and it drops quite fast, while in the collisional lines you have rings like a bubble around that other circle. Well, I'm not going to start discussing about the physics of this nebula in particular. The attempt of this video, the intention of the video is to show you how to read, just to read and make simple plots. And that's basically what I wanted to address today. In the next video, I'm going to make them shorter to digest better. We will deal with the result from the analysis of the stellar populations and the RECP's PD, the probability distribution functions based on the output of the analysis. Yeah, and that's all for today.